So what are the steps we take in detail design against stress concentration factors? First, we have to assure that all sharp notches and corners are rounded on drawings. Sharp notches mean by definition high stress concentration factors. Second, we have to maximize fillet and bend radii as much as possible. The larger the radius, the lower the stress concentration. The fillets illustrated here on the right hand side illustrate that the improvements can be made in several ways. One may try first to increase the radius, but here one should realize that the fillet doesn't need to have the full quarter of a circle. One may take only a piece of it, leaving the sharp corner at the top. The lower two cases illustrate that a fillet created with an ellipse reduces stress concentrations further. Now in practice, a sharp corner illustrated here on the left can be made smooth by adding a slope on a 45-degree angle. If we then add another slope half of that angle, starting halfway from the first slope and repeating that several times, one automatically creates a smooth transition with a low stress concentration factor. The third step is to avoid squared holes. Ellipses are better, and if necessary one may try rounded squared holes, but then take the radius as large as possible. Keep in mind that the windows of the aerial direction finder in the Comet aircraft were windows who were too squared. 4. Avoid feathered edges. The local load introduction by bolts are transferred into the component, which in combination with the radii imposes a big stress concentration factor. Instead, one should consider a continuous ring, avoiding these radii. 5. Avoid superposition of stress concentrations. As we have seen in a previous video, stress concentration factors rapidly increase when notches are superimposed. So for the example of the lug, the drainage holes should be located as far away as possible from the stress concentration. Here 3 solutions are given which all have their advantages and disadvantages. Either way, they should be preferred over the one with the drainage hole left or right. Depending on the location, one may consider beefing up the lug geometry simply to reduce the stresses somewhat further. Last, pay attention to the surface. Rough surfaces or surface markings created by machining, for example, easily increase stress concentration factors, resulting in fatigue crack initiation. To determine stress concentration factors in actual components, one may want to measure the strain gradient in order to estimate the KT. There are different methods to capture the stresses or stress fields. In any of these cases, one should consider that the peak stress at the notch root is hard to determine. In particular, if local measurements are performed with, for example, strain gauges. If one takes 2 or 3 strain gauges, one may approximate the gradient and extrapolate it towards the notch edge to estimate KT. But even with strain field measurements, stress gradient extrapolation towards the edges are required. Similarly, one has to consider that finite element analyses often give stresses which are calculated by interpolation within an element, which means that it does not represent the peak stress at the notch root surface itself. For this reason, accurate stress concentration factor determination requires very fine measures. Last but not least, because fatigue generally implies crack initiation and propagation perpendicular to principal stresses, it is highly recommended to determine stress concentration factors using these stresses rather than, for example, von Mises stresses. In all cases, comparison with approximations or handbook solutions is strongly advised. If no comparative cases are at hand, one may compare to approximations using the earlier discussed superposition principles.